Hello and welcome back. Some of you might have seen my short video on my setup for firing the big Thyratron tube. It's big, it's blue and it's scary, but it works really well, makes for a great light dimmer with Star Wars sounds to boot. This is the adult version of the video, shot in the correct orientation and where I explain what a Thyratron is and how the setup works.
And this is how the lightsaber was invented.
What led to this started quite accidentally a few weeks earlier with our initial inspection of a recently acquired IBM 650 computer at the Computer History Museum. The 650 is a historically important tube computer from the 1950s, as IBM sold over 5,000 units, an impressive record at the time. It is packed with thousands of tubes and they all belong in removable modules, each of them containing just one tube and a few extra components. You'll hopefully see a lot more of that computer in future videos in collaboration with the museum, but because of the upcoming IBM 650 inspection, Ken had spent quality time researching IBM tube modules. Turns out he even had one in his collection, but which came from a different calculating punch of the same era, the IBM 604. One day he brought that tube to the lab so we could try to power it up. In real life the 604 looks like this. And unbeknownst to me, I had a run-in with that computer in my childhood. Because somehow that computer appeared in one of my childhood comics. It's the computer that sends Tintin and his friends to the moon, visible here in the secret lab of the fictitious East European country of Sildavia. Space Race era Belgian comics references aside, Ken's 604 module is using a Thyratron, a kind of tube that is used to drive relays in the computer. It is a peculiar vacuum tube which is either all off or all on. It actually contains a gas at low pressure rather than the usual vacuum. The presence of the rarefied gas, usually hydrogen, neon, xenon or mercury, is indicated by the dot on the symbol of the tube. The gas ionizes when the tube is triggered by a short pulse on one of the grid electrodes, and the previously infinite resistance between anode and cathode drops to a very low value. The tube can switch a lot of current for its size, with extremely little current to turn it on. Once it's on, the tube stays ionized and conducting until you interrupt the current flow out of the anode, so it doesn't reset on its own. Together we built a colorful mount for the module, connected the module to a high voltage load in the form of a light bulb, and got it going with the usual assortment of filament current and high voltage supplies, which makes tube circuits slightly scary.
6.3 volts AC to the filament to heat up the filament, and we have 80 volts that's driving the tube, and then we have about 12 volts through a resistor, which is the small signal to the grid that will turn the tube on.
So your trick is you're going to turn on the big lamp with the little switch using the Thyratron.
And so the interesting thing about a Thyratron is that once the gas is ionized, you can't use the grid to turn it off. It just stays ionized. The only way to turn it off is to cut the power to the tube, which is what this switch here does.
Okay, so you have a small switch to trigger it and a big switch to stop it. So, Dr. Evil, is it time for your experiment?
Okay, so I send a little pulse to the tube.
Oh!
It ionizes and turns on the light bulb.
Oh, well, that was easy. And then to stop it, you have to...
To stop it, I cut the power with this switch. I cut the power briefly. The ionized gas stops ionizing in milliseconds, and now it's off.
Whoa, look man, it works! It turns the light on and off. But I was like, meh, it just turns the light on and off, and this little puny tube is for sissies. I also have a Thyratron in my collection, new in the box. Now that's what I call a proper tube. But it needs 23 amps of filament current and can switch 77 amps of load, which gave me pause for a moment.
How much did you say it switched, Ken?
77 amps instantaneous current.
77 amps. Okay, it's going to be interesting to fire this one up. Not sure if I'm up for it.
Later.
So this is Ken's puny Thyratron tube. And now mine is on a throw and it's all ready to go. So the way I think that's gonna work, I have the anode at, I think I set it at 200 volts, controlling 2 lamps going back to ground. Then over here I have my little trigger circuit, a little paddle, a minus 12 volt supply, and then a little bunch of resistors and capacitors. It's that small circuit that we cooked up here, which is basically the voltage across the tube with the lights and the cutoff switch, and then a resistor tied to minus 12 volts. It has to be negative apparently, not to start to fire, and then we short it to ground through a capacitor to produce a pulse and to trigger it, hopefully. But before we do that, we have to get the tube heated up. So like that, and I'm going to go maybe slowly 10 amps for a while.
What's the rating on the filament?
23 amps.
At what volts?
2.5. I have this fancy new thermal camera, which is actually very good. It's a Photrek, so it's a higher end professional thing, and the resolution is amazing. So right now, not doing much at all. So we get up to 10 amps, 30 degrees. It's not doing very much. The tube is very opaque. 15 amps, and I ran out of battery on my Photrek. Everything is conspiring against me. So this is actually the other end when it comes to cameras. Yeah, this is heating up a little bit. This is the cheap, poor in resolution, but it'll get the job done. Alright, so it's starting to heat up, and I see the mercury starting to evaporate. 18 amps. You see it? No. Oop. There you go. So we have a hot tube finally. So what happened is that I was so low, it didn't heat up, and the resistance of the filament never increased. Alright, so we go full chooch, 23 amps. It's at full current. So over here I'll get my minus 12 volts going. Alright. Then we go, it's still off, so I go 200 volts. Okay, here we go. Turn it on. Nothing happens. Turn it on. Ah, it did fire a little bit.
It just fired briefly.
And then it stopped. It did work for...
I did see a flash at the top.
Yeah, a microsecond. Now what do we do? Increase power?
More voltage.
I'm a little surprised. Or maybe my capacitor didn't like it. Okay, 250. No?
More firing voltage.
Oh, but that will drive it more negative, so because I'm driving it to...
Right.
According to the datasheet, there isn't much to this tube except for its size. It's an NL760, it can switch up to a friendly 1.5 kilovolts at 77 amps peak and 6.4 amps average. Filament voltage is rather low, 2.5 volts, but the current going through it is impressive at 21 amps plus or minus 2. You also have to heat it up over 60 seconds to make sure the filament gets to its correct resistance, and the tube has the time to vaporize the mercury inside. It does that at about 30 degrees C above ambient, so as you saw, the outer envelope of the tube doesn't get that hot at all. Only 3 terminals are used at the bottom, 2 for the filament, which is also connected to the cathode, and 1 for the control grid. The high voltage anode is at the top of the tube, once again with a max of 1.5 kilovolts. Here we will use it at a few hundreds of volts max. To trigger it, you have to bring the grid voltage above the two lines of this graph. At 200 volts supply, minus 12 volts on the grid is enough to keep the tube off, and it should trigger if the control grid is grounded, which is what my paddle switch does briefly through the capacitor. If it doesn't trigger, increasing my negative voltage supply to more negative is going to block it further. So instead I will try to do the opposite, reducing the negative grid supply voltage to see if the tube will eventually turn on. Unfortunately, you won't see me turning the power supply down because the knob is off camera. You'll have to use your imagination. But eventually, according to the spec sheet, if I end up with the grid close enough to 0 volts, the tube should trigger all the time.
Huh, why did it do it only once? There you go. So now I'm at 0. I know what's happening. So the current supply here is not able to do the current in the lamp, so it cuts out.
Right.
So I can, okay, so I have to find a stronger 200 volt power supply. I forgot this has a puny current limit, so it's a few milliamps, tens of milliamps. Okay, it works though.
Very cool.
Let me try another power supply.
So here you can see what I did to make it work. I simply reduced the negative trigger voltage supply to close to 0.
Moments later.
Okay, I'm going to try Rev 2 of the setup. So now I have those two power supplies which can do 100 voltage each, and can go, this one can go to 1 amp, and this one to 1.5 amp. It will be limited by the other one. So that should be enough to power by Q tube. And yeah, and in the meantime I've been able to recharge this. You can see how good a camera that is. It's really an excellent one. And then it has what the other cameras don't have. You can focus. Alright, so a lot of mercury has redeposited on the side of the tube, which means we had quite a bit that evaporated, which is good. 1.5 volts, not 17 amp, going down. And I see the mercury starting to disappear. 19 amps. Getting nice and warm. So now we can go to 2.5 volts, and it does its 23 amps. Now it's nice and glowy. We'll say it's good enough. So I put the output on, and it's 115, so it's now 230 volts. And there we go!
Look at that beautiful glow.
It works! Amazing. And then I should be able to shut it off this way. There we go. Oh, it works according to the spec sheet. Fantastic.
Very nice.
Oh. How often can you have with 23 amps going into a tube? I can't have both of them at the same time in the field of view, so I'll just, trust me, I'm doing the paddle, and then, wow, you can see the beautiful glow on the top of the tube. Excellent. Wow, I finally powered my big tube. And it's relatching, because on the control it's a cap, right? So just grounding it for a short moment, that's enough to get it going.
You should replace your basement light switch with this.
It's
So you can just tap on.
right. We were thinking we could make a better experiment where we power this AC and then we put an HP pulsar that's synchronized to the AC and change the angle.
So you can have the dimmer.
I can make a dimmer with it. Should we make the dimmer?
No. You don't need a side quest from your side quest.
Ah, but that's why it's electrically controlled, because you can make a dimmer. Now that I have this, it shouldn't be too difficult to
Obviously, you need to get an even bigger Thyratron next.
That's the biggest they had at Halted at the time. I bought their biggest tube.
I'm sure somebody.
And then discovered it was a Thyratron. I didn't know. It looks like some kind of fusion reactor or something, right? That's what you see in sci-fi movies. This is what's making the propulsion for the ship. Excellent. Alright, so it tells me it's 118 degrees C. Quite hot, but I mean, what's the filament at? So 500, 600 degrees C, something like that.
A little longer than a few minutes later.
So I have now complexified the setup a little bit by adding this box. It's synchronized to the 60 Hertz and it generates a pulse which I can change at what time it triggers. I can have it come at the beginning of the period all the way to the end of the period. So that's going to be my trigger pulse. It goes from here to my trigger circuit. So with the setup here, when I'm now powered by 230 volts AC, and the trigger, instead of coming from my switch, now comes from the pulsar, which is triggered by 6.3 volts AC, and then I can choose which delay my 10 volt pulse goes through, and then it goes through the circuit. Allows me to choose at which time in the cycle I trigger the Thyratron. I have now disabled the DC power supply and I am powering up in AC. So if I turn the AC on, now I am triggering at the beginning of every cycle, and it extinguishes it, self-extinguishes it when it goes negative.
So how are you synced to the AC?
I am synced to the AC via the 6.3 volt transformer of this power supply. So this is giving me 6.3 volts AC through the filament power supply.
Oh, nice.
But now I am going to retard the pulse, and as I am moving further and further away, it triggers
nice.
later in the cycle, sorry, and I have made a dimmer. Ooh.
So it only works on half of the phase, right?
Yeah.
So you're only getting 50% at max.
Exactly. To do the full wave, you need 2 Thyratrons, which is actually the usual setup. But this is what Thyratrons were used for, right? Give you control rectification. If I trigger later on, it will dim. Right? Because it's on less of the time. It really works. Amazing, isn't it?
Yeah. You should patent this. The dimmer switch will make you a fortune.
Now, of course, this is way oversized. This thing can dim up to 15 amps continuous wave, and here I have 0.5. So let's try this again. Triggering at the beginning of the cycle, and then triggering at the end of the cycle towards.
Mercury, the wonder element.
Yeah. Well, they made different ones. Where they made some with hydrogens, some with different gases.
Yeah, my little one was xenon.
Xenon, okay. Okay, I'm unstoppable. I added a current probe that's now hanging off the anode, And that's a tech current probe, and it displays on my HP scope in blue, and then you can actually see what the Thyratron is doing. Right, there it has rectified the half cycle, and then now I'm moving the pulse, and it's pinching it off. So you can really see how that's working. I'm moving the pulse in green further along the cycle, and there's less of it that gets rectified or get let through, right? And at the same time the tube is open less and less, and the light turns off. I thought, oh well, maybe we can hear what that is. Would it make like a lightsaber sound? So I have this little guy. You see, you can even make music with thyratrons. Alright, I think that will do it for today. Lots of fun with tubes that light up.
And that's how I ended up releasing a short video just for kicks, which people over in the short attention span universe don't quite get, thinking the tube is making the noise and emitting copious amount of UV and X-rays. But of course the noise is from a speaker, the UV is blocked by the glass envelope, and the X-ray comments of doom is from people using AI search instead of their own brains. No X-rays can be generated by this tube at 200 volts, nor even if we ran it at full chuch at 1.5 kilovolts. You'd require a tube running at voltages up to 15 kilovolts or more to start worrying about low-level X-ray emission. I try to explain that in the description and responding to comments, but to no avail. People don't read this in short slant, so I give up. But for you long content viewers, rest assured I wasn't X-rayed, nor did I get 2 shades darker, nor did the tube explode from vibrations. So I will be able to see you, hopefully, in the next episode.
And this is how the lightsaber was invented.